Now, first one. 6F. At the end of this lesson, I want to collect your 6A all the way to 6F. Okay? So over here we have the side view of a roller coaster track. So it goes up. So it goes down, then up, and then down. So which of the following statements are true? The total energy is the same at each of the 3 positions shown. Is that true? We assume that there are no losses. So if there are no losses due to friction, no losses due to sound, and so on, then the total energy should be the same at the 3 positions. Number 2, the kinetic energy of the car at Q is greater than at R. When it is at R versus when it is at Q. Which point do we have the greatest speed? Between Q and R. Q. Okay, who hasn't taken roller coaster before? Okay, next time you have an opportunity, right? If you can remember what you are experiencing, then you can have a better understanding. Okay? So for now, if you haven't been on a roller coaster before, just imagine. When it is at the bottom, it is going to be faster than it is at the top. So why is that so? Let's try to understand. When it is at P, suppose the kinetic energy is 0. So suppose the speed over here is 0. So it only has gravitational potential energy. And then when it goes down, gravitational potential energy decreases. So something must increase. That has to be our kinetic energy. It is just that when you're dropping a ball down, the speed will increase. Same as this. When it is at the bottom, all of the gravitational potential energy has been converted to kinetic energy. So over here, it has the greatest speed. And then when it continues up, the gravitational potential energy increases at the expense of your kinetic energy. So there is a conversion over there. You will start to lose speed, but you will gain height. So at point R, it's going to have a lower speed compared to Q. So that is for number 2. It is correct. And then for number 3, gravitational potential energy is greater at R than at P. Okay, so obviously not because R is at a lower height. So P has a greater gravitational potential energy, followed by R, followed by Q. So answer B. Okay? So for those who have been on roller coaster rides, those who haven't also, you have seen pictures of them. Why does the point R have to be lower than point P? Assuming it is a real roller coaster, why does it have to be lower, a lower height? Sound energy, you mean a lot of energy is lost, is it? Okay, lost due to heat, sound. Afiq, what were you saying? It doesn't have enough speed to climb up. That is the layman way of saying it. But what Xiao Wei and Afiq are saying are both correct. How do we improve on Afiq's answer? It doesn't have enough speed to go up. What is he trying to say? It doesn't have enough kinetic energy to overcome this height over here, because all the kinetic energy has to be converted into gravitational potential energy. So because there's energy loss over here, energy loss over here, we expect in reality total energy at R is going to be less than at P. So if it is going to be the same height, or if it is going to be higher, then the roller coaster is not going to be able to climb all the way up unless you supply energy to the roller coaster. That means maybe you supply electrical energy, like your MRT, then it can climb, can go up. But the MRT doesn't climb so high, but you get the idea, okay? Question 2, a boy drops a ball from a height. So if you ignore air resistance, total energy has to be same at all 3 points. Conservation of energy. Harif, why are you sitting there? Why are you sitting there? Huh? You can't see from there. Can you see here? Okay, next. Question 3. 80 kilogram man walks up a flight of stairs. So I think this is the second type of stairs question that you see. reaches a height of 4 meters in 16 seconds, calculate the minimum power required by the man. So the power, your formula will be work done over time taken. But we don't have work done yet, so we need to find work done, which yesterday you were not able to provide the full formula. So it's force times distance moved in the direction of the force. Must be the same direction. So the man is exerting a force upwards. That is how he is able to climb up. And what force is he trying to overcome? Shufi, what's the force he's trying to overcome? What force is the man trying to overcome? Come. Do you want to go and climb the stairs and think about what you are going to overcome? So what are you trying to overcome when you climb steps? Yanku, no give the answer. Hey, think about it. Okay, let me provide some help. Shufi, is it easy to climb stairs? In your opinion, generally. Are you okay climbing stairs? What if I ask you to carry a bag that weighs 100 newtons? So that is about 10 kilograms in mass. Is it easy? And then if I ask you to carry more weight, is it easy? It's not easy, right? So what is the force you are trying to overcome while you climb steps? What is the difference in the scenarios that I gave? Yourself climbing up versus yourself carrying something and carrying something even heavier. What's the difference in all three scenarios? The weight. So when you're climbing upstairs, you are trying to overcome your weight. So this man has a mass of 80 kilograms. What is his weight on Earth? It's going to be 800 newtons. That is the force he is trying to overcome when he climbs the steps. Okay? So the force that he is exerting will be upwards in the opposite direction of his weight, and the magnitude will be 800 newtons over here times distance moved in the direction of the force. He is exerting a force upwards. What direction is he moving? What direction is he moving? Really just upwards? When you climb stairs, do you really just climb upwards? You're climbing sort of diagonally, right? But our formula for work done states that it is the force multiplied by distance moved in the direction of the force. So suppose I'm climbing up the steps diagonally. This diagonal length, I'm going to show you on the board. This diagonal distance comprises a horizontal component and a vertical component, right? Kind of like vectors. Go from A to B. It's the same as going from A to X, then X to B. Our work done equals to force, which is upwards. Our force is upwards. Whether you are here, the force is always upwards. Times distance moved in the direction of the force. So, are we interested in AX or AB or XB as the distance moved in the direction of the force? It has to be XB. Because XB is upwards, this is in the same direction as the force. Can you understand? Who is not sure? Okay, so distance moved in the direction of the force must be the upward distance from here to here. It's X to B. I'm not going to care about the horizontal distance. Okay, but logically, when let's say you're running, okay, you're running a distance of 2.4 kilometers. You feel tired at the end, right? I'm sure there is work done, right? So work done equals to force times distance moved in the direction of force. You are just moving forward. So what is this is downwards. Okay, there is a bit of air resistance. You try overcoming. What else? Friction, yeah. So you are bringing your body forward. And there is force acting on the ground. And the ground is exerting a force on you. You are doing work on the ground also, right? When you bring your body forward. Remember your diagram about your feet, and then when you walk, those are the forces that we are interested in. Okay, when we talk about moving forward. So in this case, climbing up, we're just interested in the vertical distance, which is 4 meters. See, they only told you about the height, 4 meters. They didn't say what is the total distance he covered diagonally. Because 4, the height, is what we are interested in only. So work done divided by time taken, you get 200 watts. Okay? Then an arrow is shot vertically upwards, initial speed 12 meters per second. Over here, just highlight this. Take note that you can calculate kinetic energy straight away from here. Assuming you get the mass. Okay? They give you the speed over here. That tells you it is going to have kinetic energy. And once you have the mass, you can calculate the kinetic energy. But they now ask what is the maximum height that the arrow can reach. That has got to do with the gravitational potential energy. So based on our principle of conservation of energy, when it reaches maximum height, all of the initial energy is converted into gravitational potential energy. That means at the highest point, mgh, your gravitational potential energy, is equals to all of the kinetic energy from the start, half mv squared. Then we substitute in whatever we can. So m, we don't know. G is 10. H, we also don't know. Equals to half m, still don't know. V is 12. And we square it. Then notice what happens to the mass. Is it relevant? The mass is no longer relevant because they cancel each other out. M over here, M over here. You divide both sides by M. And you're only left with one unknown, which is H. And you find that it will be 7.2 meters. So regardless of what you throw upwards, assuming there is no air resistance, the weight doesn't matter. The mass doesn't matter. It is going to reach the same height if you provide the same initial speed. Okay, next, I have a 2 kilogram box, so that is a mass, slides from the top to the bottom of a ramp. The speed of the box at the bottom is 10 meters per second. So just indicate on your diagram 10 meters per second over here. So like I said, when you have the speed, think of its kinetic energy, half mv squared. And they gave you the mass. So all this, you must process it and realize that I can calculate the kinetic energy at the bottom now. Then calculate the total amount of energy lost to the surroundings. We can expect there to be friction between the box and the ramp because they told us specifically there are energy losses to the surroundings. Could be a bit of air resistance also, but majority of it will come from the friction that it is experiencing as it is moving downwards. So at the bottom, at the top, it has gravitational potential energy, mgh. So the height we are interested in is the vertical height here. So 210 times 6 equals to 120 joules. At the bottom, half times the mass, which is 2, times v squared, you get 100 joules. Of course, the energy at the bottom must be less than the energy at the top. So the 20 joules difference is the one that is lost to the surroundings. Answer A. Right? Can I carry on? Okay, moving on. Section B, these are the different forms of energy. Just check the answer is correct. Dry cells. Dry cells are your batteries, your AA battery, AAA batteries. It's just another name for it. Gaius, all correct? Did you write down the word potential over here? Okay, what is mechanical energy? Yeah, what's mechanical energy? What is it? It was covered in the first lesson. Who remembers what is mechanical energy? Sum of kinetic and potential energy. So A, kinetic, and everything in E. These are all your mechanical energy. Nuclear, light, electrical, they are not mechanical. Okay, next, 2A. The mass, 2 kilograms, released from the top. So initial speed is 0, height 40 meters. GPE, straightforward. Everybody should get this correct by now. Make sure you have your formula stated. Using conservation of energy, what is the kinetic energy of the ball when it is just about to reach the bottom? So your gravitational potential energy at the start will all be converted to kinetic energy at the bottom. So, assuming no energy losses, that will be 800 joules. The answer in part A is the same as part B. So with this information, we can calculate the speed of the ball just before it reaches the bottom, because 800 is now equals to half mv squared. M is given to you to be 2. So you can calculate V, and round off the 3SF, you get 28.3 meters per second. And the assumption that I just made was that no energy losses to the surroundings when the ball is falling. So in reality, would there be energy losses? What kind of energy losses would there be? When the ball is falling, there is sound? Yeah. Okay, air resistance is a force. Okay, so a bit of air resistance, that is the force. What kind of energy is lost then? What kind of energy is it converted to? Thermal energy. Because the air resistance is going to cause the surface to heat up. Can you imagine? What comes to mind when you think about something falling and then it's heating up? Meteor, right? Meteor, is it the correct word for it? Asteroid? I don't know what is the correct word lah. But basically, those rocks from outer space, then you watch movie, right? Then they fall into Earth's atmosphere, then what happens? Huh? Transformers? I don't know, anything from outer space, they just fall down. Even your satellites, yes, when they fall back onto Earth, they will start to glow and become red, right? They are heating up because they are traveling at a high speed, passing through Earth's atmosphere, which has air, and then there's a lot of air resistance that causes the surface to heat up. That is the energy that is lost to the surroundings, because it's going to heat up the air around it also. And eventually, maybe it will just catch fire, maybe it will disintegrate upon entry. The worst case is, if it doesn't disintegrate, it will just smash onto Earth. Then it will cause a crater lah. Okay? But in our syllabus, this kind of one ball falling, you don't expect too much of energy loss due to air resistance. Okay, a 40 kilogram cannonball shot vertically upwards with an initial speed of 5 meters per second is about to leave the barrel of the cannon. Then calculate the kinetic energy when it's about to leave. again, half mv squared, kinetic energy. You have the mass, you have the velocity calculation. Don't make mistakes, you get 50 joules. So assuming no air resistance, calculate the GPE when it is at the highest point. All of the initial kinetic energy will be converted to gravitational potential energy at the highest point. So the answers again will be the same. Earlier on we dropped something, this time we threw something out. Total energy remains the same in both cases. Then the highest height is given by 50 equals to mgh. So you calculate h, 1.25 meters. Yes. Zafan. Question for mass of 1 kilogram at rest initially. So initial speed 0. Initial kinetic energy also 0. Falls through a height of 5 meters, then it hits the ground. GPE, mgh, 50 joules. Same type of question. When it hits the ground, state the kinetic energy. By the principle of conservation of energy, all the energy from the gravitational potential energy is converted to kinetic energy. So no change, still 50 joules. Explanation in part 2. Basically just quoting your principle of conservation of energy. Unseen, finish? Finish? Okay, next, part C. Find the maximum speed of the object just before it hits the ground. Still using our principle of conservation of energy. Thank you. mgh equals to half mv squared. So 50 joules is equals to half mv squared. Then make v the subject. You'll find that the maximum speed, which is the speed just before hitting the ground, will be 10 meters per second. Yes, do you get this correct? Do you get this correct? Part C, yes. Owen, have you finished? Have you finished? Correct. Okay, next. Question 5. 8 kilogram crate released from the top. Sounds like what we did earlier on. Part A, calculate gravitational potential energy. Don't need to care about the slanted distance. We are only caring about vertical height above the ground. When we are calculating gravitational potential energy, they can put in a lot of different heights to different type of lengths to confuse you. You must realize that we are only interested in the vertical height above the ground when we are calculating gravitational potential energy. So 8 is the mass, G is 10, H 3, 240 joules. Then part B, the speed at the bottom is 7 meters per second. Calculate kinetic energy. So that will be half mv squared. So KE equals to half mv squared. Part B. The answer is not shown, but this is what I expect to see. Kinetic energy equals to half mv squared. They substitute in the values. You get half times 8 times 7 squared. Then what's the value? Go and calculate yourself. Junior, you have the answer right. 196. And put in the units, joules, capital J. So this is the reason why there is a difference in the amount of energy at the top and at the bottom. Work done to overcome friction when it is sliding down. So because it is overcoming friction, then there is going to be heat generated and energy is lost to the surroundings as heat. Question 6. That's not the last question. Okay, now pendulum bob mass 20 grams is released from A, then it swings down to B. The height difference between points A and point B is 30 centimeters. Okay, so part A, we want to calculate the kinetic energy of the bob when it reaches point B. Did it tell you the speed? They didn't tell you the speed at point B, so you cannot use half mv squared. But what you can use is conservation of energy. The energy at point A must be the total energy at point B. At point B, it only has kinetic energy. At point A, it only has gravitational potential energy. So, our gain in kinetic energy will be the loss in the gravitational potential energy, which is mgh. And that will be 0.06 joules. And since you have the kinetic energy at point B, you can calculate the speed of the bob using the formula for kinetic energy. Substituting all the numbers, you'll only be left with one unknown, which is the speed. Solve for it to 3SF, you will get 2.45. Okay, last question, number 7, is on power. A piano mass 250 kilograms is raised in a lift through a vertical distance of 10 meters in 20 seconds. Calculate power. So power is equals to work done over time taken. We need to find out the work done, which is force times distance moved in the direction of the force. So the force is upwards, overcoming the weight. Okay, that will be 250 times 10. That is our force overcoming the weight. And it is moved through a vertical distance of 10 meters. So that is the distance moved in the direction of the force. That is 2.5 times 10 to the power of 4 joules. How they presented it over here, what does this look like, mgh? Your gravitational potential energy, right? But did I explain it as your gravitational potential energy? No, I said force times distance moved in the direction of force. But can you see that in this case, they are exactly the same? mgh is your change in gravitational potential energy. Work done equals to force times distance moved in the direction of force, where force is mg. Your weight, distance moved in the direction of force is h. So this is one example of how they are equivalent to each other. Then power is just work done divided by time taken, 20 seconds. Leave your answer in watts because they are all calculated in SI units. Then in this lift, there are 4 60-watt light bulbs that are used for 5 hours. Calculate the total amount of energy consumed by the 4 bulbs. This energy consumed, we can consider it to be the change in energy. So power is also given by change in energy divided by time taken. So the change in energy is going to be power times time. So the amount of power will be 60 times 4 because there are 4 light bulbs. And how long were they used for? 5 times 60 times 60 seconds. Because we need to convert hours to minutes, then to seconds. This is the amount of energy used. So apparently in this question, the amount of energy used is greater. The amount of energy used for the light bulbs is actually greater than the amount of energy used to bring the piano up 10 meters. Okay? So probably not very efficient also. I don't know. Then part C, now it is pushed at a constant speed through a horizontal distance of 3 meters on a carpeted surface. When I say carpeted surface, they're telling you that there is going to be friction. So the average force of friction is 50 newtons. Calculate the work done. So work done is force times distance moved in the direction of the force. That will be 50 newtons times 3 meters, 150 joules.